Oh yeah, no, it's oh yeah, so that's why you're like crazy. Yeah, I think it's 5. You know? Yeah, like, yeah, so I can just take the final answer. And I was just like, I literally was just like, okay, go ahead and try to run it. Let me not go through.
All right, which ones now?
That's what I told you. Yeah, a lot of like my interviews,
All right. But I quit because I was spilling, because I spilled it. All right. Let's take a look at 29 and 31, please. Now, one reason I picked 29 and 31 is because they're they both come out to be the same integral. But now remember, one of the things we talked about yesterday is there are an infinite number of integrals that could describe the same piece of area. Now, right, I mean, if you shift the graph over 2 and then shift its endpoints over 2, that same piece of area is still, equal to the same number. It's in a different place on the x-axis. So if you take the one we did yesterday, natural log from 2 to 5, or if you did natural log of x plus 2, which is shifted 2 to the left, then it would be from 0 to 3. And so when you're saying here's a sigma, now write the integral that it's equal to, there technically would be an infinite number, of those that you could do with those kind of shifting ideas. And that's kind of what you've got here. So on 29, what are we looking at when we look at this sigma? Let's try to pretend, that we don't see that over here. But what this 3 over n on the outside, what's that mean? That's the width, the delta x, which is going to become the dx part, right? Then we also look at that width, and then I think the next thing that you would look at is you got square root of a bunch of stuff, right? The messy stuff. And what's the messy stuff usually? That's the x. That's where we plug in things, and that's going to be the x, okay? And so when you're looking at number 29 here, the stuff on the inside of the square root is like the x, so you think the function's probably square root of x. That'd be a good guess. And then you just start with the k equals 1, and you plug in. And so you put a 1 in for k, and you get 1 plus 3 over n. Well, okay, so what's that mean? If you have 1 plus 3 over n, and you've already guessed that this is, this part of it, so if the width is 3 over n, and the first thing that gets plugged into the x is 1 plus 3 over n, what's that tell you? Must have started at 1. Must have started at 1. Now, what I was saying yesterday, and some of the other class made a comment that I thought made a lot of sense. What we were talking about yesterday is, okay, well, if the width is 3 over n, and we have how many rectangles here? How many rectangles in problem 29? No, how many rectangles in 29? N rectangles, right? K is going from 1 to n. So we have n rectangles. So if the width is 3 over n, and you have n of those, what's the total width? 3, right? 3 over n times n. Well, see, even now I'm getting the sense that not everybody's making a lot of sense out of that. And so, so yesterday we said the total width is 3, so if you start at 1, you must end at 4. And somebody made the comment, and this makes a lot of sense, that if you're going to plug a 1 in for k, and get 1 plus 3 over n, and then plug a 2 in for k and get 1 plus 6 over n, why not then go all the way to the end and plug an n in for k, right? So let's do that. So plug an n in for k, you get 3n over n, which is what? 3 plus the 1, 4. And that tells you the ending point. And so that tells you you go from 1 to 4, and then you wouldn't have to worry about that if you're having trouble getting that other number there. And that kind of makes sense. It's kind of like when you expand it out. You put in the first, the second, you see the pattern, and then you do the end. Yeah.
So to find the beginning point then, you just plug in whatever the k or I, j they give you.
Where wherever it starts.
Oh,
Yeah.
okay.
Yeah, so now that was what the book said it was supposed to equal. Now I can see somebody else though, and I just want to go through this from yesterday, saying this. You might look at the 1 plus 3k over n, the inside of the square root, but only take this part as your x, right? Because that's the part that's changing each time. I mean, 1 plus 3k over n is changing also, but the 1 stays fixed. So if you wanted to just let this part here be the x, the 3k over n, then your integral could be the square root of 1 plus x, and that's where we got that shift, right? Well, if this part here is just being the x, whoops, wrong problem. If this part here is just the x, okay, well, when you put your 1 in for k, you get 3 over n, right? I'm not worried about the 1 right now. I get 3 over n, and then I put a 2 in for k, I get 6 over n, and 9 over n, right? Well, now where did that start if the very first thing I plugged in was 3 over n? It would have started at 0, right? Because 0 plus 3 over n, plus 6 over n, plus 9 over n. So that one would have started at 0. Now where would it have ended? Well, you put an n in for k, you get 3n over n, or just 3. And so that one goes from 0 to 3. So it's the same line of reasoning, okay? But on the original one, we were letting all of this be the x. So when we put a 1 in for k, like Dylan was just saying, we put a 1 in for k, we get 1 plus 3 over n. Oh, okay, 1 plus 3 over n, 1 width over from your starting point of 1. So either of these would have been acceptable, and I can see you coming up with either one of those as answers. Okay, now let's go to 31 here. What's different? Well, you still have the 3 over n here. You still have a bunch of messy stuff inside the square root, so you can still call that your x. Okay? But now when you put a 1 in for n, what do you get? 1 minus 1 is 0 over n, which is 0. You get 1 plus 0. Oh, okay, so the first one is at 1. Then let's put a 2 in for k. 2 minus 1 is 1, times 3 is 3. 3 over, we get 1 plus 3 over n. So the first one was at 1, the next one was at 1 plus 3 over n. Right? So what's that mean? It's still going by 3 over n, but what's our starting point? Why is ours, but it seems different, because the first thing here was 1 plus 3 over n. Here the first thing is just 1. Because it's a left rectangle. That's the difference. That's what the k minus 1 did. Now, that's not how we did. Remember when somebody said remember yesterday we had 20 plus 3i, somebody said change the 20 to a 17? That's basically what they're doing here. What was the other way we said we could do lefts? Go from 0 to n minus 1. Well, guess what? That's what this one is. So if you look at 29, 30, and 31, 29 was a right, just a basic, the very first thing you plug in is 1 plus 3 over n. So that's a right rectangle because it starts 1 width over from its beginning point. This is how a left would look, 0 to n minus 1. So you put a 0 in there, what do you get? 1 plus 0, so that's just 1. But another way to do it would be like we did yesterday. Instead of 20, we wrote 17. And that's what they've done here by putting that k minus 1. Because if you plug an n in here, what are you going to get? You're going to get 3 times n minus 1 over n. What's that equal? 3 times n minus 1, that'd be 3n minus 3 over n. That'd be 3n over n minus 3 over n. That'd be 3 minus 3 over n. 1 plus, so what's that? 4 minus, right? I gotta bring in the 1, right, from here. Okay, so it's 1 plus 3, that's 4 minus 3 over n. Well, what's that mean? Right, when I put in the last thing, that should be my ending point, right? Well, we thought our ending point was going to be 4 on this one, right? But it's a left, so where's the left? Where's the last left at? 1 width before the ending point. So that's 4 minus 3 over n. That makes sense. It's 1 width back from the ending point. So that would tell you that your ending point is 4 when you got 4 minus 3 over n. So, so that's a pretty easy one when you deal with just rights. That's the easier way to go. If you write lefts this way, I think that's an easier way to see it. It could be, a left could be written 1 to n. Okay, like we talked about yesterday. Okay, so those are the basic issues for that. All right, then we did what, 39 and 41? Okay, so 39, so this one instead of using n used 100, so what's this tell you? It says a right sum approximation, so how many rectangles? 100. There's 100 rectangle, right? What's the 2? That's the width, right? The total width is 2. So 2 100ths is the width. Notice they didn't put 1/50th, right? They didn't reduce it. I think that helps it there. And then when you put a k in for, so that's your dx. The function looks like it's going to be what? Sine x, right? You put a 1 in for k, that's 2 100ths, okay? So the very first thing you plug in is 2 100ths, which is 1 width over from 0, right? 2 100ths, 4 100ths. And then put your 100 in, you have 200 over 100, which is 2. So it must go from 0 to 2, right? So the integral from 0 to 2. So again, I'm not going to give you ones that are, I mean, just don't be looking for real tricky stuff there. It should just work out.
Insert that one then, integral 0 to 2 sine of 0.2x.
No, see, now that's where we're running into trouble. There you go. I'm glad you said that. It's just, see, where people get into trouble in these is the integral is not messy. The sigma's messy, the integral's not. The integral will not be sine of 0.02x. This is, all the messy stuff here is the x. So it's just sine of x. It's just sine of x. Okay? Because what you do, see, when you expand that out, Garrett, you take sine x, and your first right endpoint's 0.02, 2 100ths, right? You put 0.02 in for x. You put 0.04 in for x, 0.06 in for x. So that 2k over 100 is where the x was. So it's just sine of x.
So all it is integral 0 to 2 sine of x.
That's it, dx.
Oh,
Okay?
wait, never mind. That makes sense now because really all it is area. You don't need to like hit the specific.
That's right. Because that's the rectangles, exactly. Okay, what about this one? Now, what's different about this one than 39? N rectangles and n approaches infinity. So the answer to this one compared to 39 is exact area. Exact area. That one was 100 right rectangles. On 39 would have been close, but it would not have been exact. This is exact area. Okay, so what is your guess? Well, there's your dx. What's the integral? I mean, what's the function? I'm sorry. X cubed, right? The stuff on the inside is the x, so the function is going to be x cubed. And then where does it start? Well, you put a 1 in for j, you get 1 over n. So 1 over n, which is the width, 1 over n, then 2 over n, then 3 over n, must have started at 0. Put an n in, you get n over n, which is 1. So the last thing plugged in was 1. So it must go 0 to 1. X cubed, integral of x cubed, 0 to 1. Okay, so I'll give you a chance to practice a few of those here a little later, but now let's talk about 45. Okay? So, okay, 45. Now, I want to spend some time talking today about this idea of, integrals and so forth as story problems. Happy Pi Day.
Oh, yeah. Is it Friday?
Oh,
no!
Someone's doing it third
So
one.
we're-
Oh, I
this
get
off.
it.
The rumor is third block is around 4 pies.
Yeah, it could be. They said they were gonna, you could have, nobody.
Hey, if I don't have third block, we stop in.
It's like Friday.
I don't think third block will be very happy.
I'll stop in. Just tired.
All right. Now, and you want to pay particular attention today at 1:59 and 26 seconds. Right? 3:14 at 1:59, 26. Right? That's the first. How many digits of pi? I had to look that up. I had to look up the last two. I didn't know. I didn't know 159, but I didn't know the 26. That's pi out to.
Wasn't it better at 3:14? Yeah, 2 years.
Oh, that's today. Today's
Well, I know. Wasn't the time 3:14 on 3:14? Like you times that too.
No, do you do seconds?
I think it's another colon.
I think it's a colon, because 0.26 would be 26 hundredths. And that's 2660. So I think it's a colon.
Oh, so you can do it if you want to go even farther.
Yeah, with a decimal, if you did a decimal, you could go. parts of
You wait 2 years, you can go even further, because it's 3/14/15, the date would be 3/14.
Oh, that will be exciting. And then at 9:26, and then at 9:26, oh, that is gonna be fun. I'm gonna have to put off retirement.
What if it's like 70 something?
What would that be during spring break?
Oh, maybe,
That'd be so sad.
that would be something. It might be, it'll be close.
I was looking it up.
It might be during spring break.
Ask Sam Baskin, let me see that.
I'm not sure they have the schedule set for 2 years.
Sam Baskin.
Well, we'll be in college.
You guys.
So we'll just have to.
It doesn't matter, it's a Saturday.
Well, you might be back for spring break, maybe we can
It's
all
a
We can
Saturday.
celebrate here.
if we're not in
It doesn't
class.
matter, it's a Saturday.
Cassie, see what you're missing? See what you're missing, Cassie?
Prom gonna be on Pi Day. That is so cool.
Prom.
I think it's wrong.
I like pie.
All right, here we go. Let's,
We went off on a tangent.
we did, but that's, yeah. All right, part B. Now, it doesn't, I mean, we can do all of them, any of them. Which answer is most convincing? What would you have for that? Without even working it out, which of those would be a better answer? Why that over a midpoint? Because a midpoint only has 3. Trapezoid and midpoint actually are very close to being the same, because a midpoint usually has some that's over, some that's under, just like a trapezoid kind of is a closer approximation. Actually, it turns out for a given number of subdivisions, a midpoint is actually a little better than a trapezoid. And that's something we'll get into in chapter 6. But since the midpoint only has 3, you would expect the trapezoid to be better with 6 subdivisions, and definitely better than the left. Okay, but one of the things I really want to emphasize here in this is this idea right here, and we're going to talk a little bit more about that as we get into. We're going to look at some of the sample packet problems, especially as they relate to the quiz tomorrow. But if you have this, okay, if you think about this, if we think about fundamental theorem part 2. You have the integral of f prime dx from a to b. Fundamental theorem part 2 would say what? Regular f of b minus f of a. And now let's think about units. And this is where thinking about the rectangles really helps us on our story problem. Thinking about the dx is not this just thing that doesn't mean anything. The dx to us now should mean what? The width, right? Now, remember, when we do an actual integral, we're talking about how many rectangles. When we're doing the exact area, we're talking about how many rectangles? An infinite number of rectangles. So technically, an infinite number of rectangles would not have any width, right? If you could ever get to an infinite number of rectangles, you'd have 0 width. Then how would you have area? Well, exactly. Just like when you do a slope. The 2 points become 1. If they ever did become 1, you really don't want to have a slope because you'd be divided by 0, right? I mean, so they get closer and closer to becoming 1 point, just like we get closer and closer to having infinite rectangles. So the widths are getting closer and closer to being 0. Okay, so important idea. But we can actually, and I will do this for the rest of the year, when we have a story type problem like this one, okay, now they didn't even give their function a name, they just called it speed. I'm going to use f prime because we usually use that for speed a lot of times, and everything's positive, so that would be fine. So what would be the units on f prime? Miles per hour. But we can literally think of the dx as a width. If I was to plot these, what's my delta x unit? Wouldn't it? Well, it's actually minutes, and I think if you guys checked your answers in the back, you might have been off, and because there is a mixture of units that we do have to deal with here. Let me make it easier on us right now, and let me just say that it's hours. Okay? Just to make it easy for this unit example, let me make sure it's hours. But do you see how this integral should be what units? Miles. Remember we talked about if you do the area under a speed graph, it should give you the distance you traveled. I mean, we talked about that as an antiderivative, so we thought of it that way. Miles per hour, the antiderivative of that should be miles. But now it's really easy to see in an integral. It's these units times those units. We'll think of the dx as actually having units, because it's like a width. All right? So it makes sense that this would be miles. It'd be the miles at point B minus the miles at point A. And as long as we're just, it's really net distance traveled is what it is. But since everything's positive, it means we're going the same direction. It's also total distance traveled. Okay, so that's why this answer should be in miles. All right, now, we are going to have to deal with that minutes versus hours thing. Which the simplest way is to do what? Just divide by 60 when we're done. I think if we just divide by 60 when we're done, we'd be fine. Okay? Now, we could change each of these. We could change this to 0 hours. We could change this to 1/6 of an hour, 2/6, 3/6, 4/6, 5/6, 6/6 of an hour. We could do that and use those numbers instead. But if we just divide by 60 when we're done, that'd be just as easy. So if we're going to do a trapezoid, now, if I gave you a problem like this on the quiz, I would want you to, by the way, I have decided that I'm going to let you use calculators on the quiz. There isn't, I mean, any of the sigma stuff we do, you know, if I give you a sigma and want you to expand it, you have to write it out anyway. Then you can use a calculator to add them up, that's fine. Or if we're using those formulas to do a sigma, I want you to write it out and use the formula, show your work that you're using the formula. And the formulas will be on the test. Okay, the formulas will be there. So you have to write that out, but you can use your calculator to do the adding and dividing, that's fine. If I want you to evaluate an integral, if there's an integral in there I want you to evaluate, I'm going to want you to use fundamental theorem part 2. So you're going to do your antiderivative f of b minus f of a. You know, if I want you to maybe do some rectangles and compare it to the actual area, right? I want you to do the fundamental theorem part 2. You know, if you're adding up some rectangle areas, I'm going to want you to write f of, you know, like we're about to do here. But then once you write that out, you can, you know, add those up on your calculator. Well, those are the things we've been doing, right? Now, so what would I want to see on this one? So on number 1, for part B there, if you were doing trapezoid, they didn't really call this function anything. You know, we could call it S if we want to for speed, okay? So I want to see you write out for, well, you tell me, 1/2. Yeah, now, and that, no, that's a good point. I don't care, you will not have to write S of 0 plus S of 10. You know, I don't care. You don't have to do the S notation or the F notation. Now, I said that I encourage you to write an F notation. Maybe before you go and plug it into the function, it's helpful, but you won't have to. So you could write this, but it would be fine to go 1/2 42 plus 38, and then times 10, okay, plus, and then you could dot that. You wouldn't have to write them all out, right? And then you could go to your calculator and do it. But I want to see some evidence that you're doing a trapezoid situation here. So 1/2, and if you want to take the 1/2 of the 10 and put that out in front, you know, I'd be okay with that. But I'm going to let you use a calculator for the adding and stuff, but you definitely have to be writing on your paper evidence that there are trapezoids involved in what you're doing. The next one would be 38 plus 36, okay, times 10 plus ... Maybe write the last one down, okay, and then do it. All right, now don't forget we would have to divide by 60 at the end of this to turn, because now common sense, you're going for an hour and you're going, what, around 40, 50 mile an hour. So you couldn't be going thousands of miles, right? I mean, you know what I mean? If you forgot to divide by 60, you know, you gotta use common sense a little bit. You know, the data here says you're driving for an hour at these speeds, you gotta be going about 40 miles or so, you know, roughly. And so if you're getting something in the hundreds or thousands, there's no way you're going that far in an hour. So make some sense of the units. But the real payoff here, the real payoff for us, Derek and Sienna, guidance office into the period. All right. In case I forget to get to you. But the real payoff of thinking of these as rectangles, okay, besides the theoretical, you know, infinite number of rectangles makes the area, the real payoff is going to come in these story type problems, where we'll be able to set up these integrals and be able to think of units to help us with that. Okay? And each one of these, what does just this first trapezoid represent? what does that number represent? Of course, assuming we divide it by 60.
The distance you traveled.
The distance you traveled in those 10 minutes, right? So, and what's the integral doing? Remember I said we're going to now think of the integral as an adding machine, right? What the integral does is adds up those distances traveled for those 10-minute periods, right? But now, remember, those are kind of an average, right? When you do a trapezoid, that's just an estimation because we don't know for sure that it's smoothly accelerated or decelerated from 42 to 38. If it was a curve, then a trapezoid's not going to fit it exactly. So it's an estimate. What would make it a better estimate?
More.
Yeah, instead of every 10 minutes, we checked our speed every 5 minutes or every 1 minute, right? More trapezoid. More trapezoid.
More cowbell.
More cowbell, yeah, I thought that too. All right. All right. So the left, okay, would be similar reasoning. Midpoint would be. Now, why'd they do 3 subdivisions with midpoint? Why not 6 subdivisions?
So prove the point.
Wait.
Well, we don't know what you buy.
Wait. Go ahead.
We don't know like what's in each window. We don't know what like what
Yeah.
was like 5 minutes or like.
And that's very common when you have table of data. When you do a midpoint, you'll have to do fewer subdivisions because you've got to do 20 wide so you have a midpoint. So you have the midpoint in 10. So we had to do a width of 20 so we have those midpoints in there. Okay? Lefts, rights, trapezoids, they use all the data that's in there. Midpoints have fewer. So you were doing, you would use the 38, the 57, and the 55, right, in your midpoint. Okay. So that's kind of an important problem as well.
Wait, why on the third one did you only divide by?
No, well,
Is that got
well, there was only 3 subdivisions, so the width was 20.
Oh, that's
Oh, because to get
The
to an
width.
hour,
Well, no, see, okay, no, see, you took it times 10, not 20. Your width is 20 on that. Your width is 20, and then you have to divide. So you still divide by 60. Yeah, you still divide by 60, but your width is 20 on that.
You watch more cowbell shows.
Nah,
You gotta watch it.
maybe.
Yeah, Sam's always like, hey, did you watch that cool video in calculus today? I was like, no, we didn't see it.
Wait,
Yeah,
you
well,
showed the
they-
other class?
No, something came up. They wanted to some dates, mentioned something. I said, oh yeah, let's look at it.
Let's look at more
Stats.
cowbell.
And I said maybe. I think we will have time. I think we will have
Why do you like it better?
Why? I don't know where that came up, but they asked.
Well,
me. Yeah, that's a good one. No, you haven't seen it. Oh, yeah, we will look. That's what it is. All right. Okay, so let's talk about the quiz now. So if you looked at, I mean, we've already done, there's several things that we need for the quiz. All right. So where did we start? Let's just list some things, and I'll give you some problems. I want to look at the sample, some problems out of the sample packet as well, and then at the end of the period we can watch more. All right. So the first thing was draw rectangles, trapezoids. Okay. I mean, expect it to have to do that. Okay. Be able to, and maybe we can even look here. At all right, if we would look here, you know, if I give you a function, and this is the other thing, if I give you if I give you a calculator and want you to draw some rectangles, I might give you the graph, but I might just give you a function. I'll just give you a function, and then you can graph it on your calculator yourself, and then sketch it on your graph. So I think that's why another reason I want to give you a calculator. So, but just so if I gave you this function from wherever to wherever for that area, and I want you to draw 6 left rectangles or 3 left rectangles, whatever. I want you to be able to sketch neatly those rectangles, all right? I want you to be able to expand, okay? I want you to be able to expand out the sum, okay? So to me, that all kind of goes hand in hand, but, okay, I want you to expand the sum, okay? Expand and calculate. Expand and calculate the sum. All right, that's where we use that F notation. So if we're going from 0 to 3 and we're doing 6 of them, each one's a half y. So if they're left rectangles, you'd be F of 0 times a half, F of a half times a half, F of 1 times a half, F of 1 and a half times a half, right? So you would expand that out, write it out, and then you could plug it into the function and actually then add those up, get that answer.
And you said we don't enumerate all of it, just a couple, just to count.
Well, if you do, if it's less than 10, you know, if I give you 4 or 6, right? If I do F20, which I don't even expect to do, it'll be a small. So there you can write it. But if it's a sigma notation, if we're going to write a sigma notation in something, yeah, you can dot, dot, dot. You know, even, I suppose if it was 6 of them, you could go F of 0, the F of, you know, do about 3, 4 of them, and then maybe the last one, I think you should do the last one. So I'll be a little lenient on that, but write that out, expand that out, then calculate it. Now, you can leave it, and if you put it as a decimal, it's got to be 3 decimal places. If you want to leave it in terms of pi or, you know, whatever it comes out, or leave it as a fraction, that's fine too. Okay, that's always good. All right, so we want to be able to do that. We want to be able to check, obviously, we want to be able to do the fundamental theorem part 2. Okay, we want to be able to, you know, maybe compare our answer to the exact value. If it's one, we can do an antiderivative or something too. So we want to be able to do that. So you want to show that work as well. Now, yeah, you can go on your calculator and check the exact value with the integral if you want to. But I want to see the work with the antiderivative and everything. So that was some of the stuff we did the first day. And then don't forget trapezoids. If we go back to this picture here, you know, you can go back to that first homework we had, left rectangles, be able to draw right rectangles, be able to draw midpoint rectangles, okay, and be able to draw trapezoids, and including when it goes down here below the axis too, right? I mean, trapezoids like this are easy to draw, but sometimes you get the ones that are triangles, like we said. They're not even trapezoids. But
Do we count those ones as trapezoids?
But we still count those as trapezoids, and including that one we said where it went from here, it went down, it was really 2 triangles. That counts as 1 trapezoid, okay? So we did that. Then we got into the whole sigma notation. So we had formulas that will be given to you. So use the formulas, show your work. You know, if it's 15, if sigma is going from 1 to 15, you know, that's the end. You plug that in so I can see that you're using the formulas and so forth. Be able to write sigmas. You know, if I give you a pattern, if I give you a pattern of the thing, or you're asked to expand out an integral, right? 8 right rectangles for an integral, you know, f of 0 times what times, you write that out and then be able to see the pattern, be able to write the sigma. Okay, so we want to be able to do that. And that kind of filters into this stuff we did yesterday. Be able to go from an integral to a sigma, and then the one we focused mostly on today is go the other way. Be able to take a sigma and put it into an integral. And that was the one we looked a lot on 29, 31, 39, 41. We did a lot of that. Okay, we didn't really talk so much about 13, 15, you know, some of those early ones, but those were going the other direction. Right? Now there's more work to do on those, you know. You have an integral, you're going to do 10 right rectangles, you start expanding them out, figure out your width, expand them out, see the pattern, write the sigma from there. Sigmas are messy, as you expect them to be, the integral not. And that's really it. I mean, and then the last thing, I guess the big theoretical thing we learned from all this was the actual definition of an integral. And that is that a definite integral is the limit as n goes to infinity, sigma I 1 to n, f of c sub I times delta x sub I. In other words, that was a Riemann sum. The right side there is a definition of a Riemann sum. A Riemann sum is adding up of rectangle areas. That's what the right side here is, actually an infinite number of rectangle areas. The f of c sub I is just your different heights, and the delta x of I is your different widths. And as you have an infinite number of rectangles, that becomes the exact area under the curve. And so that was the whole definition that we worked on and went through. So, all right, so that's the stuff. If you can do those things, I think it's pretty straightforward from there. All right, let's just work on a couple of things here. This is in sample one. Pull out your sample one packet and let's take a look at a couple things. This was a problem we skipped. Most of you skipped, I think, in sample one. All right, see if you can come up with this here. You can talk with each other if you want to. See if you can make sense of this now. Now, I don't think it's necessary to write it as a sigma. I mean, that's what we've normally done, right? We've taken them from sigmas into integrals. So I don't think it's necessarily you have to, but wouldn't this be the sigma if you just 1 over n would go here? Wouldn't this go 1 to n? What would be inside here? What's the pattern for all this stuff? That'd just be I over n, right? So now what function are you thinking for this one? Yeah, the messy, I guess what you'd call the messy stuff would be this stuff down here. So a good guess would be 1 over x. Now, hopefully you would have come up with that without those all being there. But if you think of all that as being x, and of course your width is 1 over n with the dx, so now it's just a matter of where do you start. Well, if you plug a 1 in for I, 1 plus 1 over n, which you can tell from this, I don't think you had to write the sigma. 1 plus 1 over n, 1 plus 2 over n, so it starts where? Starts at 1, right? And goes to, if you put an n in, or if you look at this last one, it's 1 plus 1, which is 2. Wouldn't that be it right there? Now, what about the other one we talked about? If you only let this part be the x, what would change on that? You'd add 1 plus 1 over x. Now when you plug a 1 in for I, or you look at your first x, it's 1 over n, which means it would have started where? You're just looking at this part as the x, so that's 1 over n, 2 over n, so that must have started at 0. Okay? So then that would go from 0 to 1. Because they did have a 1 over 1 plus x there, but they only went from 1 to 2. I could see them doing that, though, thinking that most people would do it this way. I could see them putting in the right answer being this one, where they would have just left 1 over x from 0 to 1 like they did and not had this option. But instead, they'd have had this option right here, this 1 plus x from 0 to 1. So I think it's important, or I think it's valuable to understand both of those as possibilities. Okay, because you can see how they can do that to you in a multiple choice situation where you might have to adjust. Okay, while we're on this, were there any others in the sample packets that you had questions? I told you that we'd have some time to look at them. This would be a pretty good time. Sample 1 or sample 2? 29 we can still not do. Is that one that talks about volumes and solids? That's chapter 7. So we first have to do our lemon slicing activity before we do that. You can eat the lemons. However, by the time we get to where we're eating them, we've dunked them in beakers of water that who knows what chemical might have been in the beaker. And then we've had our hands on them, cutting them and slicing them. So, but yes, I have had people eat them. So that'll be totally up to you. I might have to have you sign a waiver or something. But, so I don't get sued. Yes, Dylan. Sample 1, number 12. This one here. Yes. This will be a good one for those of you finishing the gateway test. Now, by the way, I've went through on the gateway test and I've put in some grades for those that haven't come in to make it up or haven't talked to me. I put in kind of your best grade. For many of you, it didn't change. I mean, maybe your grade was a high C, now it's a low C or whatever, but a C and a C minus are the same thing. I mean, so I'm assuming that's what you've decided to have me do. Now, if you don't, if you want to come in and retake another one, you still can, okay? Just needs to be fairly soon, okay? Probably need to talk to me again, at some point here before spring break, okay, that you still want to try some more, okay? But here, what's wrong with this one? As far as difficulty, what's going on there? It's got this 4 there. Otherwise, it looks like an arc sine. Okay, now, this is a multiple choice, so how could you check? I mean, what would be an option? Do all these derivatives. That's not a great option. But you do all these derivatives, and even then it might not look exactly like this. Okay, remember all that simplifying stuff we talked about? So here's how you would handle this. You would take a property of square roots that you learned back in Algebra 2, which is that you can split a product in a square root like this. Right? Remember that? So what we can do here is underneath the square root there, we can take and pull out a 4. Now, we don't always do that with fractions, but wouldn't that be true if we pulled out a 4 underneath it? Now, this is something when you take Calc 2 that you'll do a lot of this kind of algebra kind of stuff because you'll get deeper into integrals and antiderivatives over we've done. But what you would do is you'd pull out a 4. Now, if you square root all that, what that means is you can square root the 4, and then you can square root the 1 minus 1/4 x squared. Like so. Now you can just pull that 1/2 out in front, and you end up with 1 over 1 minus. Now, what is 1/4 x squared? Because we want it to be 1 minus u squared, right? Right, for arc sine, we want it to be 1 minus u squared. And so what would be inside there to make 1/4 x squared? That'd have to be a 1/2 x, right? A 1/2 x squared would make 1/4 x squared, right? So this is, so if you were going to do a u substitution, you would want u to be 1/2 x here. You'd want u to be 1/2 x, and the du would be 1/2 dx. Now you can multiply the 1/2 over there as a 2. Okay, so what do I have now? I've got this 1/2 that's out in front. I forgot my dx here. My dx is a 2. That's going to cancel that. du. And then I got 1 over 1 minus, oops, that's square root. I forgot the square root there. Square root 1 minus u squared. So those cancel, and I just get arc sine of u, which would be arc sine of 1/2 x. So that's a arc sine of 1/2 x. So that's what you do when you don't have a 1. And the same thing is true with arctangent. If you had like a 4 plus x squared on the bottom and you thought, hey, that looks like an arctangent, you can pull a 4 out, make it 1 plus 1/4 x squared, and do this same kind of idea. Same kind of idea. So we can always make it be a 1 there by factoring out whatever number is there. Okay? All right, what else? Sample 2. Yeah. Yeah. That one, that's one that I should have circled before the midterm, because we should have been able to do that. We could have done that before the midterm. But that's okay. We've got some time. I think what happened was I was going through circling these. I saw area, and I was thinking it was an integral problem, so I thought we couldn't do it. It's really more of a Shanghai problem. See, you guys are still not crazy about that, right? Now, now this is no calculator, right? And that's probably what makes it the hardest. Now, this is an E. This is an E that is shifted, and instead of going this way, it's negative, so it actually goes this way, like this. Okay? So it's kind of important to have known what the picture of it looked like. Now, at the point 1E, right, that's that point right here, okay, there's a tangent line that intersects both coordinate axes. So that tangent line is going to come through like this. That's a terrible line. And come through like that. Okay, and that is going to hit, and it's going to make this trine. Well, what do we need? We need the height and the base of that trine. So we need what to get that? Why? What will the slope give us? Why will the slope help us? What do we need to be able to find this point? Equation of the tangent line. We need the equation of the tangent line is what we need. So that's why we need the slope. So we need y equals blank, x minus blank, plus blank. So we do y prime, which would be e to the 2 minus x times -1. There's our slope. We're going to plug in the point 1 and e, right? That's our point. That's our tangent point. And we're going to plug a 1 into our derivative. So if we plug a 1 into our derivative, we get -e. 2 minus 1 is 1. E times -1. So our slope is -e. Right? So now that's the equation of this line. So what is this point right here? Well, how do we get this point? Put a 0 in for x. So we get y equals negative e times 0 minus 1 is negative 1 plus e. Negative e times negative 1 is e. E plus e is 2e. So this height right here is 2e. Yeah. And then to get this point, we do what? Put a 0 in for y. So we'd have 0 equals negative. Well, the quicker way to do this would be to subtract. I'm not going to distribute that because that's going to be messier. I would subtract an e, right? So I'm going to put 0 there. I'm going to subtract an e. That's negative e equals negative e times the quantity x minus 1. Then what could I do? Divide by negative e, which would make that be 1. And then add 1. So I get 2. So that point there is 2. So now I got a triangle. It's 1/2. The base is 2. The height is 2e. Cancel, cancel. The area would be 2e, half the base time. So that's just kind of a little offshoot of the Shanghai problem, right? The tangent line. Yes. Yeah, go.
Well, basically, you just have your graph, and I knew that the point, and using that graph, there would be a point, 1, 2, and I used the slope in derivative. So at that point, the slope is negative b.
Right, gotcha.
So then I just drew a line at that point, and it would cross the y-axis at 0 at, so it would be 2e high, like that's its y-intercept. And since its slope is
Oh, so okay. So since you knew the slope was everybody hear what he's saying? Since the slope was negative e over 1, that's like rise over run. So since this is the point 1 e, if he goes up e,
over 1 plus y.
it'd be left 1, right? Because that would be negative. So he knew. Well, my picture's terrible here. But basically, since this point's at e, if you go up e, you're now at 2e. So there's your y-intercept is 2e. And then you said if you go down e and over 1, now nice. Yes. Now, unfortunately, a lot of times it don't work that nice. But that's good that you saw that you recognize that, and that's good. Okay. So that would definitely be good. And on multiple choice, man, the faster way you can get it, the better. All right. Has anybody got another one? I was going to see here if there's, I know we had some, let me see if I can find something that kind of fits in a little bit with what we're doing tomorrow. 28 on sample 2. On sample 2, go to 28. Okay, everybody see 28 here on sample 2? You can probably look at it and get it in a minute. Which one is it? B? Isn't it B? Again, width 1 over n. The messy stuff in here is the x, so it's x squared is your integral. And it's 1 over n, 2 over n. So it starts at 0, and then the last one you put in n. Well, these must be, oh, wait a minute. Well, they can't be lefts. Oh, yeah, they are. Because what would be the first left? 0. What's 0 squared? 0. They just left it out, right? 0 plus. So this is a left. Yeah, with the n minus 1, it's a left. They just left out the first one. The first left is a 0. No, it doesn't change anything. So this would still be x squared 0 to 1. So it's b. Yeah.
So it's left because
Yeah. Because if this had been right, that would have been n over n, which is your ending one, which might have thrown you off because some people would look at that and say, well, that's n over n, which is 1 minus 1 over n. Well, that's 1 minus 1 over n. So that's 1 over n, one width left of 1. But that's what it is. And whenever that happens to you, you think, well, I thought it was right. Well, sometimes the left or the right is 0. And when they're writing it, there's no sense having it in there. It'd have been easier if they would have. But. Well, the ones we do tomorrow will be more like what we've done in the homework, where it's a sigma. It's giving you a sigma. But I want you to see these in the packet as well. Okay, let's go to 43. I got one more here. And then I want to give you a few out of the book that you could work on as practice. I don't have a full-fledged review. I mean, basically your review is that stuff that's on the board there, those 6 problems. Okay? Did we do this in class? Okay, very good. All I want to comment on then on this one is how I referred to this earlier. And at the time we did this one in class, we had not talked about the rectangles yet. So when you go 300 square root of t dt, right? Isn't that how we set this up? Right? What are those units right there? Gallons per hour. What are those units right there? Hours. dt, change in time, right? Delta t, change in time. The t units are hours. Gallons per hour times hours is gallons. This integral is going to give us gallons. Now, when we go from 0 to 4, we did say that when you do that, and this was a calculator one, so you can just type it right in your calculator. Now, I'm going to say we're going to have one like this tomorrow, but this is where we're headed with this stuff. And thinking about this as a width and thinking about rectangles helps us here. This gives us gallons, but it only gives us a net gallons that it increased in those 4 hours. It was key that they told us the tank started out empty, because if not, we would have had to add that on. Okay? So this is the net gain in hours, or in gallons, over a 4-hour period. Okay? All right, very good. So, before we watch more cowbell, I would comment that if you look at the your worksheet, your sheet here down at the bottom, it's got some review problems. There's only a few. No, you're not going to do all. There's only a few in the review that I think pertain to our quiz tomorrow. All right? Now, so here's what I would write up. These are some problems that are in the book that I think could be beneficial for the quiz tomorrow, but they're not, it's not all inclusive. All right? This list is pretty much inclusive about what to do. So if you want to go back and practice drawing some rectangles, trapezoids, you can go back to that section where we did some of that. Okay, expanding and calculating, and writing that out. It's pretty easy. Fundamental third part 2, basic anti-derivatives, when I get into the hard ones here. Expanding out sigmas, that'd be like in your LH packet at the beginning of chapter 5 where you wrote out some sigmas and that kind of thing. But mostly this stuff right here at number 5, some sigma and integral practice if you want some of that. So I would say some that you could do would be, let's see, 40 and 42. Now this would be in section 5.7. This would be on page 363. So page 363, 40 and 42. Of course, you could go back and do any of 13 through 24 on that page. Remember, I had you do 13 and 15 and 19 and 21, but you could go back and do any of those on expanding out. Okay, in the review, which starts on page 366, basically, okay, number 50, number 53, 75, 80, and 118. Those 5 problems there would have to do with sigmas and integrals and so forth. All right. So those Could be some extra ones if you wanted a little bit extra to look at. Okay?